Dear colleagues, I would like to represent our talks named Spectroscopic History of the Polaris system, with my colleague Anatoly Miroshnichenko, and many thanks to our colleagues from Kazakhstan and Canada and USA. I would highlight especially Professor David Turner from St. Mary University and his student Daniel Magis, our collaborator during last quarter of century. So, spectroscopic history of the Polaris begins from the middle of the 19th century. As you can see, Polaris is a famous. Oh. Oh. Polaris is a famous navigation star, which turned out to be a variable. First spectroscopic plates was obtained in the 1670 of 19th century. The main problem to study of the spectroscopic study of Polaris is the mount, the telescope mount, because Polaris have placed near the polar axe, and very problematically to observe this star. Polaris is a classical Cepheid. What is a classical Cepheid? It is a yellow supergiants. The yellow supergiants. Their progenitors is hot B stars with masses from 3 to 30 and more. They move from the left to right in the region of red giants, and they passing out from the so-called instability strip. The region on the Hertzsprung diagram, this stars begins to pulsate. There's a form of the light changes of Cepheids. As a rule, the classical Cepheids have a more ascending branch and more smoothly descending branch. But Polaris is a small amplitude Cepheid with sinusoidal curve, and its radial velocity curve has a mirror image of light's curve. Cepheids, according to Hubble and Hertzsprung and other researchers, has a period, so famous period luminosity relation. The smallest period near 1 day and the grades of 100 and more days. This picture from our work There is an evolutionary track for Polaris. In case of fundamental mode with mass of 4.9 solar masses, and for first overtone pulsation with mass estimation of 5.2 solar mass. History of Polaris is very interesting. I repeat it. Regular brightness variation. It was was opened in the middle of the 19th century, and it was confirmed by Pannekoek. And spectral observation was begun in 1888. 10 years later, Antoni Balapolsky makes a first curve of radial velocity, and he suspects what Polaris is a binary star, and its period near 4 days he explains as the presence of orbital companion. Photographical confirmation it was by Einar Gershwin, and a long period of time, the general catalog of variable stars classificate the Cepheid as a population 2, Cepheids or Virginids. Companion of Polaris. Firstly, Polaris B is a visual companion. It was detected by the William Herschel, and from the end of the 19th to 16th of 20th century, Leaks Observatory, or the Leaks Observatory, was obtained more 1,020 photographic plates. And Moore in the 1929 founded an orbital period near the 30 years. This period is due to presence an invisible companion at the distance of the 16 astronomical units. It's approximately Uranus orbit. Why is Polaris interesting? From the point of view of astronomical astrophysical researchers, it is nearest Cepheids to the Sun. It's a very impossible object to calibrate of so-called period luminosity relation. This distance, firstly, David Turner estimates the distance near the 100 parsecs, but the distances of Hipparchus was more than Turner's results. Near results, Nelson, according to evolutionary model, has 118 parsecs, but last researchers of Gaia gives 137 parsecs. But this data based on the parallax of Polaris B companion because Polaris is very bright object and very difficult to obtain its parallax. Next, fundamental parameters of Polaris. Spectral types is spectral types is F81 is a typical supergiant, and atmospheric parameters typical for this spectral type, and gravity is very low in comparison to the Sun. Macroturbulent velocity. So, our results from the chemical composition. Observed carbon diffusion, overabundance of nitrogen, and close to the solar oxygen. According to the models for the third crossing of the Cepheid instability strip, we have a good journey with results. Our estimation of mass near the 5 solar masses. Why Polaris is interesting? Firstly, Polaris is a multiple system with a spectroscopic binary. With a spectroscopic binary, Polaris A and B, and its visual component. Moreover, Turner, approximately 10 years ago, opened what Polaris is a member of anonymous open cluster. It's a very interesting result. For Polaris, firstly, its radius was measured by the optical interferometry. And Polaris is a unique Cepheids having the largest number of the radio velocity measurements, about 3,000 during last 120 years. Precession period for this gradually increasing by the 4.5 seconds in a year during last more 100 years. Pulsation is very interesting result. Pulsation amplitude decreased from the 5 kilometers by seconds before 1950 to 1/2 of kilometer by second in the beginning of the 19th of last century. And after 1996, this amplitude began to increase again and reached to the result of 4.1 kilometer by second in this year. In 1993, the famous researcher Don Fernie from Canada published a paper with named "Goodbye to Polaris, the Cepheids." Statue of Shakespeare. This picture from his work. There is amplitude in the of light curve. As you can see, its amplitude is slowly decreased, and Fermi make a position what in the beginning of this century, Polaris is stopped its pulsation. It will be a usual non-variable supergiant. Polaris has also a magnetic field. First star for the Cepheus with estimation magnetic fields. Our observation was first estimation by Bora et al. And our results from the Zeiss telescope, their values varies from approximately from 2000 Gauss. Mean longitude magnetic fields measured by the circular polarization with high resolution 59 Gauss. Distance. The main problem of the Polaris A it's a distance to Polaris. Our results, firstly, it was we obtained the spectra of Polaris B using 6-meter telescope, and found its atmosphere parameters, absolute magnitude, and obtained the radius, mass, and mass of this companion. Our results coincide with Camper results obtained by the ground-based astronomy, and Turner results from photometrical parallax. But according to astrometry observation from Hubble Space Telescope and Gaia satellite, this distance more for the approximately 40 parsecs. And this data allows to speculate about evolutionary status of Polaris. One position. Is a distance of near the 100 parsecs when Polaris pulsates in the fundamental tone and crosses the Cepheid instability strip for the first time. In case of Gaia distances, Polaris pulsates in the second overtone and crosses Cepheid instability strip for the first time. If Polaris pulsates in the second overtone, the huge age difference between the components. For example, 75 million years was estimates the age of the main component, where for the Polaris B, 2.1 gigayears. There are three alternatives to explain the discrepancy if you assume the parallax applied to the four stars. Polaris B is not physical coeval companion of Polaris A. Polaris B is a physical companion of Polaris A, but it is usually luminous, very luminous. The system age is 2.1 gigayears, and Polaris A could be descended from the blue straggler which merged in the past. To resolve this problem, we have a Knight's move. Accordingly to Turner, Polaris belongs to the open clusters. In this case, we can check the distances using main sequence stars in the Polaris clusters. If you know our if you know effective temperature, readings, and distance, we can get the radii of these components, of these main sequence stars, and check how well they correspond to the relation of effective temperature, luminosity, and radius calibration for emerged stars, according to Mamayev and Turner. As a result, our radii match for 8 stars, while one half of solar radii to 3 solar radii different from the remaining 10 stars. And it was a conclusion. Gaia geometric distances are overestimated for the 56% of the probability clusters members. It's very interesting. Look, there is distance and radial velocity, our estimation for the stars in the Polaris field. The majority of stars have a radial velocity estimation close to the Polaris, and some stars have a more radial velocities, and these stars are members of a thick galaxy disk. And this is an interesting result. Numbers of stars. If you can see, these 2 peaks. And this picture we interpret as a presence near the Polaris, 2 open clusters dissolved in between the stars of Polaris field. Oh, it's our there's look on this picture. There is a distance for Polaris stars. There's stars belongs to the Polaris open clusters, and 2 stars from our list is stars of thick galaxy disk. And turned out there is observational minus calculation data, and there is distances from the Gaia DR3 catalog. As you can see, approximately 9 stars have photometrical distances what coincide with Gaia data, and other is have more large estimates. As a result, we can explain this the distance from Gaia DR3 is not correct. Thank you.
Yeah.
Can I have a question? Sure. Okay. Do you think that the wrong estimation of Gaia is because it's too bright, this star for Gaia?
It's not only for Polaris, it's also some field stars. So we see that O minus C difference.
Oh.
So there are problems with Gaia.
Okay.
All right, so let me continue, and I will show you a strange slide. I used to be an amateur 50 years ago. So I just fell in love with astronomy in 1973, and I started doing some strange things, some of which are listed here. So I was stargazing. I was copying stars on paper from just my binocular. I didn't have a telescope, and this was one of my activities. So it's in Russian, it's in Cyrillics. I was assembling some lists of bright stars, and I had no idea what it was can be used for. But the bottom line is that, especially at a young age, people can be interested in many things. And I think I kept that wide field of interest until now. About 25 years ago, we started the collaboration with Igor on Polaris star, and just 2 slides about the same observatory, just different aerial view of the Free College Observatory. We started that collaboration when I was working at the University of Toledo, and we took a few, maybe, 10 to 20 spectra of Polaris before this century. And then there was a gap in that collaboration because we didn't have any equipment. And since 2012, we continued observing Polaris. So this is another view of our telescope. This is what we get. Our spectra start at about 3800, and the red edge is 85, sorry, 85. We extract 33 orders, and then they all overlap, and you can actually, by fitting the orders with simple polynomials, using the IREF software, you can produce one spectrum, one stitched spectrum. One thing which I do a little bit better than some large telescopes, observatories, like, for example, CFHT. So when they do their stitching, they don't cut the edges, the ends of the spectra where the signal-to-noise ratio is the lowest. And as a result, there are some mismatches between orders. So I typically cut some parts of the blue edge and some part of the red edge, and there is still enough overlap to stitch it without losing significantly a signal-to-noise ratio. So here is a typical spectrum of Polaris. It's an late F-type supergiant, so there are many lines, and because of that, it's pretty good for measuring the average velocity and amplitude of pulsation. And by the way, so what we use here is an 81 centimeter telescope equipped with the Shell axis Shell spectrograph. The detector is ATIC 486 EX camera. And for, I believe, maybe 4 to 5 minutes, doing several exposures. Usually I do 10 to 20 exposures on Polaris and then sum them up. So the signal-to-noise ratio in the continuum can get as high as about 300 and even more probably in the blue region. We were measuring the average radial velocity in two ways. One way was using some other software, measure individual radial velocities and then average them. But more recently, I figured out that we can do actually cross-correlation, and cross-correlation can work very good. So I assembled a calculated model of a star with temperature very close to Polaris. So you can see the variation of the temperature of Polaris over the pulsation cycle. It's about 100 degrees. Then we roughly know the gravity there, and I just did several calculations with different projected rotational velocities. And you can see that the model spectrum is very close to the observed one, and this is the region in which I did cross-correlation. And by the way, you don't need to match your template spectrum with the observed spectrum very precisely. Even if there is a difference in the temperature of your whatever template spectrum is and the actual spectrum of the star you study, you will be just losing accuracy if there is a bigger and bigger mismatch, the lower and lower accuracy. In this case, it was pretty good, and in this spectral region, there are several dozen lines. I got an average error, an error in the average velocity of about 300 meters per second, which is actually the precision of measuring radial velocities with this assembly. Over the years, we were finding little changes of the period and larger changes in the amplitude. So here are typical phase curves for the radial velocity variations during several pulsation cycles. It's 4 days, but this range of data may be 2 to 3 weeks. Despite we are located very close to the sea level in a very, not very, but relatively humid region, we have every other night clear. And for spectroscopy, you don't need to have perfect nights. So sometimes, even when it's cloudy, I can do Polaris. And since about 2015 to today, we got about 600 spectra, and I believe it's the largest collection of at least recent and electronic spectra. But it gave me trouble. In the middle of April, I tried to observe Polaris very close to the lower crossing of the meridian. And there is a gap in my tape which transfers the tick marks to the coordinates. So the telescope lost orientation, fibers got around the mount, and they got destroyed. So now we have a period of idle time, and when I'm back home, the Shellyak people will send us new fibers and retune the guiding unit which rides on the telescope. So this is 2016. This is the latest set of data in March, April 2024. You can see that the sinusoidal fit is very good, but it's obvious even by the eye that the amplitude in 2016 was lower than it is now. So the amplitude keeps increasing. The pulsation period is about the same. Even 20 years ago, Igor collected about 2,000 estimates or measurements of the radial velocity and did Fourier analysis, which resulted in several peaks in the power spectrum. So this is the main pulsational mode. Then another peak was at 3.2, which turned out to be a second overtone. mode. Then there was another peak. So because this is kind of pulsating thing, you can expect all kinds of periods. For example, this one is a beat period between these two. And then there are some longer periods found which were attributed to some spots on the surface, but there is no confirmation so far. It's one of the hypotheses for those long periods. So these people and Igor, they found very similar periods, but we still don't know what this period is about. Then if you go back to the pulsational mode of Polaris, turns out to be dependent on the distance, because models of stars, of Cepheids with different luminosities predict pulsation in different modes. So either it's the fundamental mode or overtones. And there is still at least dichotomy between the distance of about 100 parsecs and this is the Hipparchus distance, which was corrected by van Leeuwen in 2007, but it's not much different. Those different distances lead to different absolute magnitudes, and therefore, from models, it follows that Polaris pulsates in different fundamental modes. All right, so there are different techniques to deal with changing periods, and one of them is to have some kind of ephemeris, some period, and then calculate the difference between that one moment period, which I think was observed in the 1920s, and the period at some other epochs. So this is what was going on with Polaris. So the period was increasing by a few seconds a year on average, and then it started decreasing. But something happened in the 1960s when interest to Polaris was almost lost. So all of a sudden, the period dropped by about 1 minute, and we still don't know what happened because there are not many observations. Since that time, interest got back, and this is what we are getting closer to our time. But there is some at least a hint for a deviation from this about parabolic curve. And here is a close-up. This is from the paper by Guillermo Torres from Harvard Smithsonian Center, which was published 2 years ago. So some changes, and it's interesting to see where it would lead us to. Now, if you get to the orbit of the inner binary, so as a matter of fact, it's really hard to resolve that inner pair Polaris AA and Polaris AB. But from the radial velocity, we can definitely assemble an orbit. And these high-frequency oscillations are pulsations, and on top of that, there is long-term change due to the orbital period of about 29.5 years. So this is some orbital. These are orbital parameters from a paper by Evans and collaborators, 2018. When we decided to do a similar analysis, we came up with a little different solution. So these three colored curves, they show solutions from different sources. Our solution is in red, and then there are some other previous calculations. And you can see that they're not much different given that scatter due to pulsations. But the most recent data, and the red data are our data from this year, they show that probably we need to correct the orbital solution even more, because those those points, which at least I believe in them, because we observe many stars at our observatory, especially every night we observe radial velocity standards. So we know that our wavelength scale is correct. So maybe after another few years, we will recalculate the orbital solution for the binary, but not much of a change is expected. On the other hand, in science, we always strive for more accurate results, which sometimes allow us to better understand the processes. So here is the last cycle of the orbit. Most of this data come from our observatory, and you can see that the most recent data, 2023, 2024, here's 2022, they are a little bit lower than what is expected from all of these solutions. Since we know the orbital parameters, we can calculate the mass function, which I think you know that it comes from Kepler's law plus Newton's law of gravitation. So if you have a binary star, so M2 is component number 2, M1 component number 1, it is affected by the inclination of the orbital axis with respect to line of sight. So this is sort of its theoretical part, but the observational part is here. So our orbital period multiplied by the semi-amplitude of the radial velocity variation. If there is an eccentricity, it should be taken into account. So we know all these parameters, and we can get this number. But this number depends on the masses and on the tilt angle. Each of this colored curve corresponds to different tilt angles. So 90 degrees is that black one, so that pink one is 80 degrees, 70, 60, and so on. From the dynamical masses, so this way we can determine dynamical masses, which are listed in this paper. So that's for Polaris A, this is for Polaris B. We can figure out roughly the inclination angle of this system, which is about 35 degrees. Now, the paper by Evans et al., they used Hubble Space Telescope, and this is image from Hubble of Polaris AA and Polaris AB. So they were able to measure the angular distance between the stars, and then if you know the distance towards the system, you can figure out the separation. This is the astrometric orbit of Polaris A. The main component is here, Polaris AB is here. So sometimes when you have a few points, but you still have a spectroscopic orbit, this solution may be pretty accurate, but sometimes you really need points over here. So a periastron occurred in the second half of 2016, and it is here. I'm just not sure that anybody is going to be given time at Hubble to do new measurements. If you if you assume some distance, I think here I assume the distance of 100 parsecs, almost no interstellar extinction, average brightness, then you can put Polaris in the Hermite-Russell diagram and compare its position with evolutionary tracks of single rotating stars from the Geneva group. And you see that the mass of Polaris is about 5, maybe 6 solar masses, but that's evolutionary mass. Dynamical mass coming from other considerations, including the Hubble observations, is about 4 solar masses, and this is, I don't know how to reconcile that, because at 4 solar masses, they don't, stars are not supposed to have these excursions through the instability strip. So that's a question for maybe theorists who do evolutionary calculations. And this is what Igor was talking about. If you assume I think it if you assume Gaia distance, then Polaris is here. Some other Cepheid is shown for comparison here, and Polaris B here. These are isochrones for certain masses of stars, and Polaris is supposed to have an age of about 100 million years, but Polaris B is supposed to be a lot more evolved. So there is a discrepancy which again can be solved by assuming that these are not a physical pair, or the distance is different. So kind of several puzzles going on with Polaris. And this is a change of the amplitude, full amplitude of the radial velocity variations. This is a picture from Torres, the most recent paper on this orbit. And this is what I got from the table which Torres sent to us for the periods. And here are the red points are recalculated amplitudes from cross correlation. So these are also same points, except for the last 2 years, because we published our results on the orbit in 2020. And we used a different method of averaging radial velocity, and it turns out that it led to different amplitudes. I believe that this one is more accurate, and if it's true, then the amplitude of Polaris is gonna keep increasing. But there was that little kink. So another sign of that the nature is more complicated than models that we run. So here I come to conclusions. Basically, it's turns out to be a very interesting star, but you cannot observe it from everywhere. For example, I've been going to at the Observatory San Pedro Martir in Mexico. They have 2-meter telescope, but they cannot point to places more northern than about 70 degrees declination because of the amount. So Polaris cannot be observed there. So we are going to keep observing, and perhaps at some point when we figure out whether there is a cluster around Polaris, we may be able to constrain the distance even better. But maybe Gaia finally, after several more orbits, will correct their parallax scale and will come to a better solution for Polaris. But still, they cannot observe it, and maybe special treatment for such a bright star is needed to extract the parallax. So these are conclusions, and the last thing I wanted, if we have time.